Hello and welcome back to Stats. So we're going to continue on with sort of conditional probabilities here and independence and a few of the other topics that we talked about last time. So we're going to start with the multiplication rule for independent events. And you may or not remember, but last class we talked about the general multiplication rule, which is when you wanted to know the odds of two events happening. Is the probability of the first one times the probability of the second one, given that the first one had happened. All right. Well, when two events are independent, we can simplify this a little. All right. So two independent events. All right. So if you have two independent events, the probability that both will occur is, again, that's and. The probability of A times the probability of B. All right, we don't have to mess around with the conditional. Now, why don't we have to mess around with the conditional? Well, if we remember, again, on that previous sheet, we said the general rule was this: A and B equals the probability of A times the probability of B given A. All right. Now, we talked about the definition of independent. All right. These two values are equal when the events are independent. All right, so we don't have to worry about the conditional piece because these two are entirely equivalent when two events are independent. All right, so again, it just gives us sort of a simplified version of this sort of concept of multiplying probabilities together. When the events are independent, we don't have to worry about this conditional piece. All right, so let's see how this kind of plays out, or let's see examples of this. So battle plan. A general can plan a campaign to fight one major battle or three small battles. He believes he has the probability of 60% of winning the large battle and the probability of 80% of winning each of the small battles. Victories or defeats in the small battles are independent. The general must win either the large battle or all three small battles to win the campaign. Which strategy should he choose? So you're basically talking about the probability of winning a large battle, which is 0.6, versus the probability of winning three smaller battles. And since they are independent of one another, we can just do 0.8 times 0.8 times 0.8, which, if you can't do that in your head, that's what the calculator's for, 0.512. All right, so in this case, you'd go with the one large battle. All right, you have a better chance of winning that one large battle than you have of winning three independent small battles. Even though each one has an 80% chance, the combined probability is going to be lower than the one large battle. Next, a string of lights contains 20 lights. The lights are wired in a series so that if any light fails, the whole string will go dark. Each light has a probability of 2% chance of failing during a 3-year period. The lights fail independently of each other. What is the probability that the string of lights will remain bright for 3 years? All right, and this is a situation where we can sort of take advantage of the complement. So what is the probability that the string of lights will remain bright for 3 years is basically saying, what's the probability they all stay on? All right. Now, if they have a 2% chance of failing, that implies they have a 98% chance of not failing. Now, for the lights to stay on, all 20 have to not fail. So we're basically saying, what are the odds that all 20 don't fail? So this is 0.98 times 0.98 times, and we would do this 20 times, or to be a little more mathematically sophisticated, 0.98 to the 20th power. Now, whichever way you write it, it's still the same idea. But we're basically saying, all right, if they have a 2% chance of failing, they have a 98% chance of not failing. We need all 20 to not fail if we want the string of lights to remain bright. So 0.98 to the 20th power gives us 66.76. So 0.6676 or 66.76%. So you basically got a 2/3 chance that the lights will stay light for 3 years. Because remember, according to this, if even one of them goes out, the whole string goes dark. So we need them all to stay on, and there's basically 2 out of 3 chance that it'll stay on for the full 3 years. The first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a 2005 study, approximately 5% of normal pregnancies will receive a positive result. Among 100 women with normal pregnancies, what is the probability that at least one woman will receive the false positive result? All right. So again, presumably each woman is independent of another woman. So we can assume this rule right here. So we don't have to worry about conditional probabilities. And again, this is a situation where at least one woman is actually kind of difficult to figure out. All right. Because that could mean one woman has it, 2 women, 3, 4, 5, 6, 7, all the way up to 100 women have the false positive test. Again, another situation where it's easier to calculate the complement and then reverse that. So the opposite of at least one woman having a test is the probability that no one has a false test, right? And that's a much easier probability to calculate. And then we can just flip it around. All right. So if 5% of normal pregnancies receive a positive result, so that means a false positive. So if 5% are false positive, 5% are false positive, then 95% are fine. So we're basically asking, what are the odds that all 100 people are going to end up with the correct result? So it's kind of like what we did up here. We can just say, all right, that's 95 to the 100th power. All right, so 0.95 to the 100th power is 0.0059. All right, so this right here is the probability that no one has a false positive. It's an awful looking arrow that I just drew there. Sorry about that. All right. Now, if we want to know what's the probability that at least one, we can take the complement of that. So we can do 1 minus 0.0059, end up with 0.9941. Right? And this is the probability of at least one false positive. All right, and again, the complements make this a much more manageable problem, because otherwise we'd have to find the probability of one false positive, add it to the probability of two false positives, add it to the probability of three false positives, add it to the probability of four false positives, all the way up to the probability of 100 false positives. And we'd have to add those all together. It's much quicker to say, all right, what's the probability that nobody has a false test? And then just flip that around using the complement to arrive at our answer here. So again, yes, this idea of independence, you don't have to worry about conditionals, but also this idea of complements and how we can use that to sort of manipulate the question and make it easier or more manageable for us to calculate or consider. All right, mutually exclusive events. All right, what are mutually exclusive events? They are two events that cannot occur together. All right, we saw this with our Venn diagrams. These are the ones that don't overlap. So a lot of times, once we introduce the term independent, kids start getting confused between mutually exclusive and independent. What's the difference? Are they the same thing? Are they not? So can mutually exclusive events be independent? Here's an event. Person is male. That's our event A. Event B, person is pregnant. Are those two events mutually exclusive? I think most people would say yes. Males cannot become pregnant. Now, if we were in school right now, I would show you the trailer to the movie Junior, starring Arnold Schwarzenegger. So if you are at home and you would like to pause this video and search out the trailer for the movie Junior, starring Arnold Schwarzenegger, you can see that there is a single exception to this, a hilarious exception. I encourage you to watch. No, I don't encourage you to watch the movie. But yes, all right. Being male, being pregnant are mutually exclusive. If one happens, the other can't happen. Are these two events independent? All right. So let's remember what we said, what our test was for independence. We're saying that for two events to be independent, the probability of A, is it the same as the probability of A given B? All right. If I say, what's the probability of being male? You probably would say, yeah, it's about 50-50. And then I say, all right, if I tell you that the person is pregnant, what are the odds that they're male? You're going to say 0%, right? So you just showed that the events are not independent because you probably started off with like, okay, it's probably about 50-50, so it's probably about 50%. But once I tell you they're pregnant, you're going to say, oh, the probability that they're male is 0%, or Arnold Schwarzenegger. So the events are not independent. All right, they are not independent. And that's always going to be the case when you're dealing with mutually exclusive events. Mutually exclusive events cannot be independent because as soon as you know one exists, the probability of the other one happening drops to 0. All right. So, and the whole thing about independence is knowing one piece of information doesn't impact your opinion on the other. Mutually exclusive is the exact opposite. As soon as you know one piece of information, you know the other event is impossible. So that is exactly the opposite of independence. So a lot of times kids confuse these and think they're the same thing, when in actuality, they're about as far apart as you could imagine. All right. Mutually exclusive says once you know one is true, the other can't be true. All right. Independence says once you know one thing, it doesn't impact your opinion on the other. All right. So they are not independent. knowing B changes the probability of A. All right. So I get why they're confusing because we've been dealing with all these different formulas and everything, but here's how it breaks down. When two events are mutually exclusive, all right, so this is our OR situation. The probability of A or B goes from P of A plus P of B minus P of A and B. This is where we subtract out the double counting to just the probability of A plus the probability of B. All right. There is no double counting when events are mutually exclusive because there's no overlap. So we just get to get rid of this part right here. When two events are independent, that's what lets us simplify our multiplication formula. Probability of A times probability of B given A drops to just probability of A times probability of B, because we know when two events are independent, these are equivalent, so there's no need to worry about the given A part. All right, so again, two terms that a lot of times kids get mixed up, but they have radically different implications and they have radically different meanings. So going back to our original question, can a mutually exclusive events be independent? Never. All right, so just try to keep those straight in your head. Mutually exclusive is referring to two events that can't occur at the same time. There's no overlap in your Venn diagrams. So if we've got our Venn diagrams here, it's like two separate circles. Whereas independent isn't related to this. It's, all right, once you know one, does it change the odds of the other happening? All right. So let's move on to the conditional probability formula. All right, which is going to kind of combine a lot of the different stuff that we've been doing together. All right, we're going to look at some tree diagram stuff with this. We're going to look at some Venn diagram stuff with this. We're going to look at some of the formulas and kind of use them all. All right, this is also big in what's called Bayesian reasoning, which I think is pretty interesting because it just sometimes it leads to sort of like non-intuitive results. And it can kind of question the way that you think about like likelihoods of events and certain things happening. Anyways, to find the conditional probability, P of B given A, use the following formula. The probability of B given A is the probability of A and B over the probability of A. Now, it doesn't take a whole lot of algebra to see that really this is just that same formula we've already been using. So our general multiplication formula was the probability of A and B equals the probability of A times the probability of B given A. All right. If you divide both sides by the probability of A, you end up with our formula here. All right, so it's really just that same multiplication formula that we've been using. It's just you're sliding the terms around a little bit. All right, but let's see how we can use it. All right, so it says, use the Venn diagram below to find the probability that a person who reads the New York Times also reads USA Today. That is, find the probability that a person reads USA Today given that they read the New York Times. All right. So the probability of reading USA Today given that you read the New York Times. Now, using our formula here, we can see that the given goes to the bottom of our fractions. So whatever given here is going to the bottom of our fraction here. So down here is going to be the probability of reading the New York Times. And then the top here is both of them. So what's the probability of USA Today and the New York Times? So we can get this information from our Venn diagram here. The probability of reading both, they tell us, is 5%. The probability of reading the New York Times is this whole circle right here. So that's 25%. So that means our final probability here is 0.05 divided by 0.25, which is just going to be 1/5 or 20%. All right, so this is the probability of reading USA Today given that you read the New York Times. All right, so if we kind of intuitively think about what's happening here, think back to our two-way tables. All right, we're forcing you to say that, okay, we're only looking at the New York Times people. That's why this is the bottom of our fraction. And then we're saying, all right, if we just look at the New York Times people, what portion of those read the USA Today? That's where our 5% is coming from. And then we're getting our conditional probability that way. All right. So again, this probability of USA Today given the New York Times. All right. And we're going to be able to use this formula in different ways depending on the information that's available to us. And depending on which of these three pieces we have, we can solve it sort of in different directions. So here's a tree diagram, right? And this is the same tree diagram we made in our notes last time. It's the kind of video sharing tree diagram. So this says, what percent of adult internet users who visit YouTube are age 18 to 29? All right, so we can't get this directly from just looking at these numbers, but we can use our conditional probability formula. It says, this is saying, what's the probability of being 18 to 29 given that you visit YouTube? Now, how did I know that that was my given? Well, it's in the sentence here. It says, what percent of adult internet visitors who visit YouTube? So that becomes our given because they're telling us that they're visiting YouTube. So that's going to become, again, this goes to the bottom of our fraction. The given goes to the bottom of our fraction. So it's going to be the probability of YouTube. I'm just going to abbreviate it there because I'm running out of space, over the probability of 18 to 29 and YouTube. All right. So we can see here 18 to 29 and YouTube is going to be this branch right here. All right, so it's this one over to this one. So that gives us the 0.27 times 0.7 over the probability of YouTube, which is really 3 branches in total. All right, it's this branch, and this branch. So we're going to need to look at all 3 of those. So what that means is we're basically looking at 0.27 times 0.7 plus 0.45 times 0.51 plus 0.28 times 0.26. Now, the chart actually gives us all of these values. So the first one, or the top of our fraction, is 0.1890. The bottom of our fraction is going to be 0.1890 plus 0.2295 plus 0.0728. And then if we add those together and divide, what do we got here? So 0.1890 divided by 0.1890 plus 0.2295 plus 0.0728. We'll say 38.5, so 0.385 or 38.5%. All right. So that's saying that of all the people that visit YouTube, 38.5% of them are ages 18 to 29. And again, we're kind of using this table to sort of work backwards and answer a question that's not immediately obvious, but we can find using this formula here. All right. So let's take a look at one more. And again, we'll read it and then we'll go from there. Over 10,000 athletes competed in the 2008 Olympic Games in Beijing. The International Olympic Committee wanted to ensure that the competition was as fair as possible, so the committee administered more than 5,000 drug tests to athletes. All medal winners were tested, as well as other randomly selected competitors. Suppose that 2% of athletes had actually taken drugs. No drug is perfect. No drug test is perfect, sorry. Sometimes the test says that an athlete took drugs when they didn't. This is called a false positive. Other times the drug test says an athlete is clean when they actually took drugs. This is called a false negative. Suppose that the testing procedure used at the Olympics has a false positive rate of 1% and a false negative rate of 0.5%. What's the probability that an athlete who tests positive actually took drugs? Now, I can't force you to do this, but what I'd like you to do is estimate what you think the answer is going to be. All right, we're going to run through it in a second, but just estimate for yourself what you think this answer is going to be. Because it turns out that we're usually not very good at making these sorts of estimates. And I'll explain why after we do the problem, because I don't want to give away whether it's high or low. But make an estimate, and then we'll see what we end up with. All right. So we're going to start with a tree diagram. All right. The first thing we're going to look at is the drugs. All right. So it tells us that 2% of athletes had actually taken drugs. Now, obviously, we couldn't actually know this information. We don't know everyone that's tried to cheat or that did cheat, but we're using that as our estimate. So we're saying that to the drug question, 2% said yes, which means that 98% said no. All right, that's our starting point. Now, once that has been established, then we have our test, all right? Then we have our testing section. And you can either test positive or you can test negative. And the same is true if you didn't take drugs. You could not take drugs and still test positive. That's called our false positive. Or you could test negative. Hopefully you will test negative. That means the test is working. So in this case, the test is working. That's what we want to see. All right. In this case, the test is working. That's what we want to see. But there's these two situations in here where the test kind of screws up. We took drugs and it tells us we're negative. We didn't take drugs and it tells us we were positive. Now we can get those from up here, right? It says, suppose the testing procedure used at the Olympics is a false positive rate of 1%. So false positive means it's saying that you're positive when you didn't take drugs. So that's this one down here. So there's a false positive rate of 1%. which means that most of the time, or 99% of the time, it's getting it right. Now, over here, it tells us we have a false negative rate of 0.5% or 0.5%. So a false negative means we took drugs, but it doesn't catch it. So this would be 0.005, which means this is when you did take drugs, it's getting it right most of the time, 995. All right, so if we wanted, we can find the likelihood of each of these events. All right, this one would be 0.02 times 0.995. This one would be 0.02 times 0.005. This one would be 0.98 times 0.01. And this one would be 0.98 times 0.99. All right, now, what is this question actually asking? It says, what's the probability that an athlete who tests positive actually took drugs? So they're saying, what's the probability that you took drugs given that you tested positive? All right, well, from our formula, we know that's the probability of testing positive, because the given goes down to the bottom of your fraction, over the probability of taking drugs and testing positive. I got to space these things out better. Too much room over here, not enough room over here. All right, so let's abbreviate that and slide it over a little bit here. So the probability of D, the probability of D given P, or the probability of taking drugs given that you tested positive, equals the probability of taking drugs and testing positive over the probability of just testing positive. All right, so the probability of taking drugs and testing positive is this one right here. All right? We took drugs, we tested positive. So that's our 0.02 times 0.995. All right, this again is took drugs, tested positive, over the probability of testing positive. Well, there's two different places where we test positive. So we've got this one right here, and we've got this one right here. Both of those were positive test results. So we've got the 0.02 times 995, same as above, plus the 0.98 times the 0.01. All right, so this is same as above. This one right here is no drugs, but a positive test. All right, so if we multiply these out, we've got 0.02 times 0.995. So that gives us 0.0199. And then the bottom is just that same number again, plus 0.98 times 0.01, or 0.0297. So again, if we drag this down here, the probability of taking drugs given that you've tested positive is 0.0199 over 0.0297, or 0.67. So what that's saying, the real world implication of that is only 2/3 of the people who tested positive actually took drugs. Now, I don't know what your estimate was when you started, because this is a video and you're not in front of me actually telling me, but I'm going to guess that it wasn't 2/3. All right. It was probably like, oh, yeah, most of the people that tested positive took drugs. But this is saying a full 1/3 of those people didn't test drugs. And the reason people usually get this wrong, the reason people are usually off, is that they focus on the accuracy of the test. And they say, wow, well, the tests are super accurate, so most of the people that test positive must be guilty. And they ignore the base rates, right? They ignore these base rate probabilities that say 98% of the people didn't take drugs. Only 2% of the people took drugs. So even though that there's a really tiny chance of getting this false positive, it's a tiny chance on a much bigger group of people. So it ends up making up a pretty significant portion of this group, almost 1/3 of it. Yes, this is really high, but it's a really high proportion of a much smaller group. All right. So it leads to this counterintuitive result of like only 2/3 of the people who tested positive actually took drugs, because we underestimate the impact of this initial probability, this fact that only 2% are yes and 98% are no. And we miss the fact that, yeah, even though these are accurate, they're acting on a much bigger sample. Like down here, they're acting on a much bigger sample. Up here, they're acting on a much smaller sample. Think of it as like 1% of a million versus 99% of 100. All right. 1% of a million is a much bigger number than 99% of 100. But people tend to focus on the 99% and the 1%, and they miss the million and 100. And that's kind of what's happening here. And that's why you end up with this sort of non-intuitive result where only 2/3 of the people who tested positive actually took the drugs. All right. And that's what I was saying before, is how you can end up with some non-intuitive results when you actually force yourself to kind of go through and perform these calculations. Intuitively, our brain is not good at coming up with this type of number. We have to go through and put in the work to actually see the result that comes out of it. All right. So that's it for today. Again, just kind of like recapping, we've got a formula that sort of shortens up when the two events are independent, because those pieces are equivalent. We've got this idea of sometimes using the complements to make our lives easier, especially when you're dealing with an at least one situation. At least one is usually pretty hard to calculate. It's much easier to find the probability that no one meets the condition and then just flip it around. We've got this idea of sort of the difference between mutually exclusive and independent. And then last but not least, we have kind of our conditional probability going on here. All right, where we can use this formula to come up with and perform different calculations and sort of see what's happening on that front. All right, so I hope this was useful. As always, if you have any questions, just let me know and we will go from there. All right, have a great day. Bye.